So let me introduce the last speaker of today, Professor Michael Hochman from Hebrew University. Professor Hochman did his PhD at Hebrew University and gonna talk about dimension of self-similar sets and measure.
Okay, thank you. It's a pleasure to be here. So this is the dynamic section, and in fact, there's not going to be so much dynamics in this talk. I want to give a survey of recent results on these objects, self-similar sets and measures. And there's been a very big development over the past decade. Many problems have been solved or partly solved, and I'm not going to have time to talk about all of them. I'm going to focus on one, what is maybe the principal, most basic problem of computing the dimension of these objects. I know that most people here don't work in this area, so I'm going to start by explaining how these objects could come up in a dynamical setting. They come up in many ways. Let me start presenting this in terms of random walks. So, you start working in RD, in Euclidean space, d-dimensional space, and you choose finitely many similarity maps, F1 up to Fk. And let's assume, to avoid trivial cases, that there are no common fixed points to these maps. And you choose a probability vector P1 up to Pk, which you should think of as a distribution on the maps. So you're going to choose random maps according to this distribution. Again, to avoid trivial situations, let's assume that all the PIs are positive. And now you define a random walk on RD by choosing some arbitrary initial point x0. You start at some x0, and then to go from xn to xn plus 1, you choose a random map, xi n plus 1, which is independent of all the previous ones, so you're actually choosing a sequence of these maps independent according to P, and you apply the map to xn. And so you started at x0, you applied a random map, you got to x1, you applied a random map, you got to x2, and you're doing a random walk on RD. And it's very natural to ask, what is the behavior of this random walk? So roughly speaking, there are three types of behaviors that you can observe. And I'm going to omit some of the details about the exact assumptions that you need. But the first case is when you have isometries, when all the maps are isometries. And then what you expect to get is the central limit theorem. That is, if you look at the distribution of xn at time n, it's some probability measure, discrete probability measure on RD, and if you scale it by root n and translate it and perhaps apply some affine transformation to correct for the covariance matrix, the distribution converges to a Gaussian, to the standard Gaussian. You also have a local limit theorem which says that under some mild arithmetic conditions, on any bounded open set, if you look at the distribution of points at time n in that set, they will converge to the uniform distribution on that set. And so there are several phenomena here. One is that you have a universal long-term behavior in which the limiting distribution is almost independent of the data that you started with. It almost doesn't depend on the maps, only up to a covariance matrix. It doesn't depend on the probabilities. You get the same thing no matter what you do. And what is happening is that the points are spreading out in the most random way that they possibly can. Locally, they're converging to Lebesgue measure. Globally, they're converging after normalization to a Gaussian, which also has very nice properties. Okay, the next case you could consider is when the maps contract. And then the situation is very different. So first of all, because of contraction, you can actually show that without any rescaling, the distribution of the random walk at time n is going to converge to some measure mu, some probability measure mu on RD, called the stationary measure. This is actually a self-similar measure. But the measure depends very strongly on the data that you started with. And by choosing different maps or different probabilities, you can change how the measure looks and how it behaves. And so we'll talk about that more soon. And so you do depend very strongly on what the system was that you began with. And the third regime, which I won't talk about very much, but I want to mention briefly, is the case where the maps expand. And if the maps expand, the random walk is going to go off to infinity very quickly at an exponential rate, and there's not going to be any reasonable way to rescale it so that it converges on R D to any kind of reasonable distribution. But what you can do is you can look instead at the directions in which they're going off, and then you get to boundary theory. So there is going to be some limiting distribution to the directions that the points go off in. Again, and you'll get some distribution on the space of lines, the space of directions, which will not be universal. Again, it will depend on the initial data. And in fact, these last two cases are very closely related, because if you look at the action on the space of lines, it will be contracting on most of the space. So the last case is, in some sense, it's not a special case of the first case, of the second case, but it is closely related to it. So we're going to focus on the second case, on the contracting case. So the limiting distribution that you get from this random walk is called a self-similar measure, and it is characterized by this equation. Mu is equal to the average of its images under the FIs, where the image under FI is just the push forward of the measure under Fi. And so this gives you some implicit equation of what mu is. Most of the talk will focus not on the measure itself, but on its support. So the topological support of mu is called a self-similar set, and it's the unique non-empty compact set that satisfies a similar equation. X is the union of its images under the Fis. Okay, so this is one way of defining them. Now let me show you the easier way to define these attracting sets, these self-similar sets. It's just a Contra Set Construction. So you start with your system of maps, your FIs. Because they contract, if you take a big enough ball or a big enough square, they'll map the square into itself. So here is a big square, and you apply each of the maps to it. Suppose you have 3 maps in this example. And you get 3 copies of the big square inside the big square, but scaled down according to the contraction of the maps. Now if you take this picture, you take these 3 squares, and you apply each of the maps to those 3 squares, to the union of those 3 squares, you'll get copies of those 3 squares inside each of the 3 squares. Now you have 9 squares, and you can keep going. You can apply each of the maps to the picture that you had, and in the limit you're going to get, by intersecting all these unions of squares, you're going to get some closed, some compact set, and that is the attractor. That's the self-similar set. It's not always a Cantor set, that is, it doesn't have to be disconnected. It sometimes isn't, it sometimes isn't. It depends on the system of contractions that you chose. So this is the way you would introduce this subject in an undergraduate course on fractal geometry, and it's really the simplest kind of construction that you can do to get an object that looks the same at all scales, maybe up to some rotation and translation. And so it's a little bit embarrassing that we don't know how to compute the dimension of these things, but in many cases we don't. Even though it's sort of the textbook example of a fractal set, we don't always know what its Hausdorff dimension is. Okay, so one question is what is its dimension? And for the measure, you can ask the same question. I didn't say. So what is a measure? You take the same construction, but at each stage you give weights to the squares according to the probability vector that you started with. So P1, P2, P3, and you iterate that. So you distribute the mass of the larger square to its 3 children according to the PIs, and in the limit you get a probability measure that sits on this limit set, on this attractor. Okay, so you can ask what is the dimension of the measure. We define the dimension to be alpha if the mass of a ball of radius r scales like r to the alpha at almost every point for the measure. And you can also ask if the measure is large enough, whether it's smooth, that is it absolutely continuous with respect to the big measure? And if it is absolutely continuous, you can ask how regular is the Radon-Nikodym derivative? Is it bounded? Is it continuous? Is it smooth? Is it L2? And so on. Okay, and so the sort of guiding conjecture, which is at this point in quotation marks because I haven't defined things yet, is that the random walk should spread out as much as it possibly can, and correspondingly the measure should be as smooth as it possibly can, and the attractor should be as big as it possibly can, unless there is some algebraic obstruction to this happening. And this type of philosophy, you might recognize it from many other settings in dynamics. I mean, it's similar to Ratner's theorems. It's similar to rigidity theorems for diagonal flows that exist in part today. Benoit stiffness theory is another statement of this kind. And so this is a variant, very different of these rigidity phenomena that happen in algebraic settings in the contracting world. Okay, so to make this statement precise, to make this conjecture precise, I have to tell you what it means for something to spread out as much as possible. That is, how much could it possibly spread out? And I have to tell you what the algebraic obstructions could be. So here's the classical result, which is usually attributed to Hutchinson and possibly Morin, and of course before there were special cases. And I should say that I apologize if I don't mention so much of the history because I simply wouldn't have time otherwise to say anything. So there is a candidate for the dimension of the attracting set, which is called the similarity dimension. If we denote the contraction ratios by R of I, then the similarity dimension is the solution to the equation sum of Ri to the power s equal to 1. And Hutchinson proved that the dimension of x is always bounded above by s. And if you make the additional assumption that the union of the images of x are disjoint, this is called strong separation, then the dimension is equal to s. You can relax this slightly to something called the open set condition, but I don't want to discuss it. Okay, and there's an analogous statement for measures. So under the separation assumption, we know what the dimension is. Then the problem is solved. And when we don't have separation, we at least have an upper bound. And the upper bound can be slightly improved because the dimension is not only less than s, less than or equal to s. We also know that we're a subset of Rd, so the dimension is at most d. So the upper bound that we know trivially is that the dimension is bounded by the minimum of s and d. We're going to call this the trivial upper bound. And if the dimension is strictly smaller than this number, we're going to say that the system has dimension drop. Okay, so let me very briefly explain where this number comes from. It's just counting. So you assume that you have 3 maps and they contract by a quarter. So in the first generation, you have 3 cubes of side length 1/4, and in the second, you have 9 cubes of side length 1/16, and so on at stage n. At generation n, you have 3 to the n cubes of side length 1/4 to the n. And what is dimension? Okay, hand waving, you're asking how many cubes of side r do you need to cover the map, and what power is that of r? And so, without actually doing the computation, with these asymptotics, you see that the dimension is at least log 3 over log 4, which is s if you actually plug it into the formula that I gave before. Okay, so this is, again, what you do in the first undergraduate course in dimension theory. So I've told you why it's an upper bound. I haven't told you why it's an equality. And the equality comes from the fact that because the pieces are separated, you can't do much better than to take these squares to be your optimal cover. You can't improve on that very much because you can't get 2 of these groups inside 1 square this size because they're separated. Again, that's hand waving, but that's more or less the truth. So why is it only an upper bound? Because suppose that you have here's a different example where you have some overlap between the pieces. And when you iterate it, this overlap propagates to the next generation. And at generation n, you're going to have exponentially many small overlapping pieces. And what could happen is, what we were doing before is we were just counting how many small rectangles we have. But when you have overlaps, that may not be the most efficient way to cover the set. It may be that when you have overlaps, it's better to take a rectangle that's slightly bigger and covers both of them in one go. Right? So it's really hard to understand what these overlaps do. And it's a little bit misleading because it looks like these guys are overlapping, but when you get closer, you might see that the overlap actually goes away when you go to several generations down. So the difficulty here is that, okay, we can't count it well enough. That's the difficulty. We just don't know how to estimate what the best cover is. That's life. Okay, so, but I have explained just now one reason why the count, you could get an overcount. It could be that you don't need actually all of these guys to cover, or maybe you could do it with a slightly bigger one to cover 2 of them. But there's an even more extreme case, which is maybe at some small scale, 2 rectangles exactly coincide. If they exactly coincide, you can throw one away. You don't need to count it at all. Okay, so we're going to call that the situation when there's exact overlaps. More precisely, suppose if you have a sequence of indices I1 up to In from our index set, and you look at the composition of the maps Fi1 up to Fik, I'm going to call that just F sub I is the sequence. And we're going to say that there are exact overlaps if there are 2 sequences of indices that give you the same compositions. You can compose the maps in 2 different ways and get the same map. Okay? Which is just to say that these maps Fi don't generate a free semigroup, or they don't freely generate the semigroup that they generate under composition. So this is an algebraic property. It's just saying that there are no relations between, well, exact overlap means that there are relations between these maps. And as I said before, it's a simple observation that if you have enough such coincidences between the maps, if enough of those small rectangles are actually the same one, then when you're counting how many rectangles you need to cover the set, you don't have to count all of them. If there are enough coincidences, the dimension will go down. So the precise conjecture that was in quotation marks before, I'm stating it for dimension 1, is that exact overlaps are the only cause for dimension drop. That is, conjecturally, if you don't have any algebraic relations between the maps, the dimension should be as big as it can possibly be, namely it should be equal to the minimum of the similarity dimension and D. And the evidence for this conjecture mostly comes from, or well, at least results in the, I guess, 90s gave some support to it by studying parametric families of systems. So it's very difficult to show for an individual system which has some overlaps that it has the correct dimension, but you can study parametric families and show that for most parameters, the corresponding self-similar set has the correct dimension. And so there are many such results. Okay, so to state first theorem, I have to quantify what it means to quantify the distance between compositions of maps. So we're going to fix some left invariant Riemannian metric D on the group of similarities. And this is the right metric to take, but it's maybe not the most natural or intuitive metric to take. Many other metrics you could take will work equally well for these definitions, and some of them are more pleasant. In any case, let's just choose a left invariant Riemannian metric, and then let's define delta n to be the closest that 2 compositions of length n of our maps come with, as long as they have different, as long as the compositions are different. That is, we take 2 words of length n over our family of maps, different sequences of words, and we take the smallest distance of those 2 maps to each other. And you can make some simple observations. One is that this sequence is decreasing, or at least it's not increasing. Having exact overlaps means precisely that for some n, the minimal distance is 0 because you have 2 compositions that are the same. In fact, it's also easy to see that if this is true for some n, then it will be true for all large enough n. And not for the left invariant metric, but for some choices of metric, you can also, as you might expect, have a fast decay of delta n to 0, exponential decay to 0. And so we'll say that the maps are exponentially separated if there is some positive number rho, so that rho to the n bounds delta n from below. So the compositions that you get by composing n of the maps can come very close together, but there is some exponential, very small exponential lower bound on the distance between them. So this is essentially a Diophantine condition. Okay, we'll talk about that more later. And what metric you choose will certainly affect the value of delta n, but having this property of exponential separation is fairly insensitive to the metric that you choose. So if you choose a right invariant metric instead of a left invariant metric, or if you choose a norm, if you think of the similarity group as a matrix group and take a norm on it, the property of exponential separation is robust under those changes of the metric. Okay, so this is something I proved a few years ago, which says that if in dimension 1, at least one of the following is true. Either you have the full dimension, the expected dimension that you would have if you were separated, or you have super exponential decay of delta n, which in other words just means that if you have exponential separation, then you don't have dimension drop. So recall that the conjecture was that if you don't have exact overlaps, you have no dimension drop. Okay? So we still don't know how to prove the conjecture. But this allows us to establish that the dimension is correct in many cases where we couldn't do it before. And there is an analogous statement for measures, which I don't want to make simply because it's a little bit more difficult to explain what the similarity dimension is for measures. It's not hard, but time is precious. Okay, so let me state one corollary of this, which is that in dimension 1, if you restrict yourselves to families of contractions where the coefficients of the FIs are algebraic numbers, so the FIs are similarities, so it's a matrix and a translation and some contraction ratio. If these numbers, all the entries of these vectors and matrices are algebraic, then in fact dimension drop implies exact overlap. Okay, so then in that case the conjecture is true. And the reason for this is very simple. Suppose that there are no exact overlaps. It's possible to choose the metric in such a way that the distance of two compositions of length n of the functions is a polynomial in the coefficients of the functions, and the degree of the polynomial is n. For example, if you take, I don't know, the L2 norm would probably do the square of the L2 norm. In any case, so this is a polynomial expression, and a polynomial expression of degree n in a fixed number of algebraic parameters is either 0 or it's exponentially bounded away from 0, where rho is some number that depends only on the coefficients that go into the polynomial. And that means that since delta n is equal to such an expression for some pair of sequences, that means that you have exponential separation, and therefore you have no dimension drop by the theorem. So although we don't know the conjecture in general yet, we do know that it's true in the world of algebraic similarities. Okay, so a few words about higher dimensions. The conjecture and the theorem are false as stated in higher dimensions because there are other algebraic obstructions that can happen besides non-freeness of the semigroup. What do I mean by false? You can have a drop in the dimension and have no exact overlaps and even have no exponential separation. And what happens is that the new thing that can happen is that you could have invariant lines or invariant line fields for the maps. And so here's how that can happen. So I'll describe to you how to build a finite system of contractions where, in 2 dimensions, where what was stated before fails. So let's start with some very small number r. And let's start with 2 maps. I take the large square, I map it down to the 2 corners of itself. Okay? And now I'm going to add more copies of it in the column above this guy. Okay? I'm going to add lots of them. I'm going to add so many that it covers the entire column above the lower left corner. And then I'll add the same on this side. So I'm going to take a huge number n, a huge number n of these maps, of these little squares. Many more than 1 over r. And if I want to, I can arrange that, for example, the heights of these squares could be rational or could be algebraic. So I'll ensure that way that I have exponential separation in the system. Okay, now, simple calculation shows that the similarity dimension of this system is just the log of the number of maps over log 1 over r, and that's going to be a very big number. Okay, it's more than 2. Now, okay, so what's the attractor going to be? What's the self-similar set going to be? Because I cover the entire column, at each step of this iterative process, I'm going to have the entire column over some set of intervals in the base. And in the limit, I'm going to get simply the product of some Cantor set x1 in the base times an interval. Okay? And the dimension of x1 is going to be less than 1 because it's a Cantor set. It's a regular Cantor set. And so the dimension of the product will be, in this case, will be the sum of the dimension of the base, which is less than 1 and 1. That's going to be less than 2. And it's going to be less than the minimum of 2 in S because S is bigger than 2. Okay? So you have a counterexample here. You have exponential separation. The similarity dimension is bigger than 2. You have no exact overlaps, but the dimension is too small. But what happens here is, first of all, the foliation into vertical lines is invariant under these maps. And the extra dimension that you were expecting to see got absorbed in these overlaps in the columns, or in the limit, you would say that it sort of got absorbed in these vertical lines. And these vertical lines intersect the self-similar set in a set of dimension 1. Okay, and so that is what one would conjecture in general. So let ui denote the rotation of the similarity fi. Okay, so fi is a rotation, a scaling, and a translation. So ui is the rotation part. And so the conjecture in higher dimensions should be that one of the following holds, maybe more than one. Either the dimension is as expected, or you have exact overlaps, or there is a subspace V of Rd which is invariant under the UIs, and a point in the attractor so that the intersection of the attractor and the translate of the space through that point has full dimension. It has the dimension of the subspace itself. And what we can prove now is that this is true if you replace exponential separation with, if you replace exact overlaps with super exponentially close or super exponential decay of delta n. So when I put a question mark by publication date, it just means that it hasn't been published yet. So there will be several more citations like that later. So as a corollary of this, if the rotations act irreducibly on Rd, then the third possibility isn't possible unless the dimension is already d. That is, unless V is Rd itself. And so in this case, when the UI act irreducibly, what you see is that you're back in essentially the same statement as in dimension 1, where exponential separation implies that there's no dimension drop. And I would mention that there is a related result to this by Lindenstrauss and Varyu, I think from around the same time, from 2014 or so, which used completely different methods, assuming that the rotation matrices have a spectral gap, so that means that we're in dimension 3 or up, and assuming that the contraction is weak enough and that the entropy of the probability vector P is high enough, they show that the measure is absolutely continuous, and so has full dimension, has dimension D. So under strong enough information, you can improve this statement not from full dimension to smoothness. But there's still quite a gap between the assumptions that you need for smoothness and the assumptions that you need for full dimension. And we also don't know how to establish spectral gap in most cases. Okay, so I won't be able to say very much about the proof, but let me just give a very, very vague idea in one slide, okay? So assume that there's no dimension drop, and let's go to some small scale. So here is our overlapping system of contractions, and we go to some small scale. And now, locally, if you look at just one small piece of this picture, what you see is many copies of the original. I mean, okay, I started with a rectangle, but if I had started with the attractor itself, I would see many copies of the attractor, or of a measure on the attractor, perhaps. And in this example, I have some rotations, but if you suppose for a moment that I don't have rotations, or that all the rotations are the same, all these little rectangles will be pointing in the same direction. And then, and I can choose, okay, and I can, if I have smaller dimension than I expected, that means I can choose this ball, I can choose some ball, in fact, typically any ball that I choose will be good, so that I have exponentially many small rectangles here. Not just lots of them, but exponentially many. Exponentially many in the scale that I'm looking at. And so now, if all these guys are translates of each other because they're pointing in the same direction, and I have exponentially many of them, and I have a measure on each of them, then the measure that I see here is actually a convolution of the measure on one of them, and an atomic measure which has exponentially many atoms. And exponential separation will tell me that those atoms are not too close together. And now you're in the world of additive combinatorics, where you take a convolution of two measures, or perhaps the sum of two sets, and you want to say that unless they have very special structure, the size of the set will go up under this addition operation, or some quantitative version of some quantification of smoothness of the measure will go up under convolution. And if you can show that, then when you look at the covering number at a smaller scale than this, you will see more than you should see. The convolution will cause entropy to go up, or taking a subset will cause the covering number to go up dramatically, and you will get, at a slightly smaller scale, a much higher covering number than you expected, and this will give you a contradiction. Okay? So, okay, that was sort of much too fast, but I mean, the key idea here is, the thing to understand here is that the key ingredient in all of these proofs is to analyze what happens under to measures under convolution, and to show some quantitative result about how the smoothness increases under convolution, which is a classical thing too. Okay, I want to say a few words about one of the main applications of this that's seen a lot of development in the past 3 or 4 years, and that's the subject of Bernoulli convolutions. So this is an old problem. I'll give some of the history on the next slide. It concerns a family of measures. So you fix a parameter lambda between 0 and 1. And then you define a measure nu lambda, which is the distribution of the random number, which is defined as this random series. And what's random here is the signs. So you take plus and minus for each index n, or each index k. You take the plus and the minus independently with probability 1/2, 1/2. And so you have a random series, random power series in lambda with the signs chosen randomly, and this random number has some distribution. And now if you write this power series with you take out the first term, plus minus 1, and then you write it as plus lambda times the original series. Well, it's not the original series because these signs are independent of this sign, right? These are the shifted signs. These are the signs that started at index 1 here. In any case, if you condition on the first sign, then what you see is that the distribution of this random series is the average of the distribution of this random series scaled by lambda and translated by 1, and of the distribution of this random series scaled by lambda and translated by -1, which is exactly the identity that I wrote on the second slide. You exhibit nu lambda as an average of its image under two affine maps, under two similarity maps. And so nu lambda is a self-similar measure. And we would like to know how smooth it is. So the trivial upper bound using the analog of similarity dimension tells you that for lambda, at least for lambda between 1/2 and 1, the trivial bound is 1, so, which doesn't tell you anything really. But potentially, you could have equality. And you might expect that the dimension is 1. And so what we'd like to know is this measure of dimension 1, is it absolutely continuous? Of course, absolute continuity would imply dimension 1. So a very, very, very quick history. So I think this subject was first studied by Jessen and Wintner in the mid-1930s. They proved laws of pure type, which say that this measure is either absolutely continuous or singular. It can't be a combination of two such things. The first sort of surprising result is by Erdős in 1939, and he noticed that using Fourier analysis, he showed that if the inverse of lambda is a Puiseux number, that is an algebraic integer greater than 1 whose conjugates are all of absolute value strictly less than 1, if lambda inverse is a Puiseux number, then the measure is singular. And Garcia later showed that its dimension is actually less than 1. And Salem showed that, in fact, if you measure smoothness in terms of decay of the Fourier transform, then smoothness is equivalent to the inverse of lambda being Puiseux. And so these things have led to the conjecture, although I don't know to what extent people are convinced of it, but certainly it's been suggested that the inverses of Puiseux numbers are the only parameters between 1/2 and 1 for which nu lambda is singular. There was a paper in here by Kahan, which I've omitted, but in any case, Solomiak in 95 proved that absolute continuity holds for almost every parameter lambda in this range. And it was slightly improved by Peres and Schlag to show that the dimension of singular parameters goes to 0 as you approach 1. Okay, so using these methods which I described before, or outlined before, there's been a lot of progress recently. So to begin with, a fairly simple application of the main theorem which I stated shows that the parameters for which nu lambda has dimension less than 1 has dimension 0. So not only almost every parameter will give you dimension 1, but in fact the exceptional ones have dimension 0. And shortly after this, Pablo Schmerken improved this to show that the dimension of the singular parameters is actually 0. And both of these, the first result, both of these results use the fact that you can show that the maps that define nu lambda have exponential separation outside a family of parameters of dimension 0. And the absolute continuity comes from an additional clever Fourier theoretic argument that uses the convolution structure of nu lambda. And I want to mention two more recent results. So up until 2 years ago, there were only two classes of numbers where we could actually verify that nu lambda is absolutely continuous. One is roots of 1/2, which are sort of trivial, and the other was a class of numbers found by Garcia, of algebraic integers found by Garcia, where you have very good control of power series with alternating signs in them. But recently, Peter Value proved a very surprising result that shows that many algebraic lambda, in fact, give you absolutely continuous Bernoulli convolutions. So the statement is the following: for every epsilon, there's a constant c, so that if lambda is an algebraic number with Mahler measure mu lambda satisfying that lambda is bigger than 1 minus c times the minimum of the log of the Mahler measure and the log of the Mahler measure, the power minus 1 minus epsilon, then nu lambda is absolutely continuous. As I said, this gives a very large class of new examples where we know absolute continuity. And another even more recent result by Boyal and Value gives a very surprising reduction of the problem of dimension of Bernoulli convolutions to the algebraic case. So what they show is that if you look at the set of lambdas for which the dimension is less than 1, so these are the exceptional parameters for dimension, then in fact this probably shouldn't be an equality. This should probably be they're contained in any case in the closure of the algebraic exceptions. So in principle, in order to determine whether the only exceptions are Puiseux numbers, it would be enough to show that the only algebraic exceptions are Piso numbers, or inverses of Piso numbers. And the way that they proved this, okay, I mean, both these results are very complicated. They are based on quantitative estimates on what exponential separation gives you in terms of the entropy of finite approximations of these measures. And there's some number theoretic input and other very clever arguments. So I won't go into that. Okay, so just to end the talk, I want to talk about some other results that have come out of these methods. And as I said, or perhaps I didn't say, in the last decade, there's been a lot of progress on self-similar measures. It began, in fact, with a result of Schmerken and Paris, or Paris and Schmerken, on projections of self-similar sets. And so the first result, so that used completely different methods. One result that came out of these methods was improved results on the smoothness of projections of self-similar measures by Schmerken and Solomiak. Another result with Solomiak is a similar statement for the Furstenberg measure or boundary measure for random walks by affine maps on R2. So, as I said at the beginning, if you look at maps which expand or partly expand Euclidean space, the random walk that I described in the beginning will not behave well on RD, but it will behave well on the space of lines. In fact, it will contract typically on the space of lines, and you arrive at similar problems. And so in R2, when you do a random walk, the direction at which the points go off to infinity will distribute for some measure, and we were able to show that this measure also is as large as it should be in some cases, in many cases. Another result that used at least a similar philosophy is a result by Schmerken, which solved what's called the Furstenberg slice theorem. This is or conjecture. Yeah, this should be a conjecture. The theorem is Schmerken's and Wu's. The conjecture said that if you take a self-similar set in the plane, let's say with strong separation, and let's say that all the rotations and contractions are the same, and you intersect it with a line, then there is similarly an upper bound on what you expect the dimension of the line to be. And the conjecture was that this upper bound is always true. That is, there's an upper bound for typical lines, and what Pablo showed is that the lines always are as small as you expect them, or possibly smaller. And this relied on a very similar approach to analyzing the projections, sort of the dual problem, analyzing the projections of such sets, using again a very similar philosophy of applying additive combinatorics methods, but measuring smoothness in a different way, plus some other ideas. And I'll mention that Wu proved the theorem simultaneously in using other methods. Another direction which I'll just mention two more recent works, one of them in progress. If instead of similarities you consider affine transformations of the plane, then you leave the world of conformal dynamics and you're in the world of non-conformal dynamics, and estimating dimension becomes much more complicated. So we recently showed that for self-affine sets and measures, you have the same theorems, that if you assume you have the analog of Hutchinson's theorem. If you assume strong separation, there has been for a long time an upper bound on the dimension, which is due to Falconer in the 80s, and we recently showed that under assumption of strong separation and some mild irreducibility assumptions on the matrices, this is the correct dimension. And very recently in work in progress with Rappaport, we can do the same thing assuming exponential separation. There is an interesting feature there, which is that in the case that the matrices are not totally irreducible, there is a new algebraic obstruction, which is that you have to exclude the possibility that the set sits on a quadratic curve. So somehow it's possible for the random walk to be attracted to an algebraic curve, and you have to exclude that explicitly. It can happen. So such examples were, I think, first shown by Bant and Kravchenko. Okay, but I'll end just by saying that the main conjecture is still open, and many things have been solved, but the main conjecture, I'll just go back to it maybe, is entirely open, and somebody still needs to solve it. Okay, thank you.
Questions? Comments? So let's thank the speaker again.